Hey everybody, this is Dr. Ban again. Just going over a couple of problems. This is the homework chapter 13 to the end. Um, and one of the problems that students had was on this one, review question 1323. The question was, a reaction has the following rate law. Rate is equal to K A squared times B times C. It's asking you for the units of the rate constant K. So the first thing to remember is that rate is always going to have units of molar per second, or concentration over some unit of time. And molar per second equals some rate constant times A squared times B times C. And of course, these are in moles per liter as well. So this would be moles per second equals K, and this would be molar concentration to the fourth power. So molar squared times molar is molar to the fourth. So the units, in order to give us molar per second, the units for the rate constant have to be molar cubed per second. Okay? And that would give us, so molar per second equals, this would be molar per second. So molar cubed and molar to the fourth. If I cancel that out, I get molar on top and seconds on the bottom. So the answer for this one is going to be liters cubed per mole cubed per second, which is the same thing as per molar cubed per second. Okay. And then 1368 was another problem that we had. So the concentration of a drug in the body is often expressed in units of milligrams per kilogram of body weight. The drug is eliminated metabolically by a first-order process having a rate constant of 2.97 times 10 to the minus 3 per minute. What must the initial dose of the drug be in order for the drug concentration at this time, 3.27 hours afterward, to be 5.2 milligrams per kilogram of body weight? So we know that this is a first-order process. Okay, and so it's asking us to determine the initial dose of the drug. So, and the initial dose is going to be a concentration. So it's asking us for A initial, and equals some rate constant kT, A at some time t, and we have this equation that you have to memorize. Natural log of A0 over AT equals kT. That's a natural log. So I'll write ln. And A initial divided by A at time t. In this case, that's going to be 5.2 milligrams per kilogram. That's our 5.2 milligrams per kilogram equals the rate constant in this case, which is 2.97 times 10 to the minus 3 per minute, times t, which is 3.27 hours, and we can convert these hours to minutes. So there's 60 minutes per hour. Hours cancel, minutes cancel. Okay, so go to our calculator. We've got 2.973 negative times 3.27 times 60 is 0.5827. 7 equals the natural log of A0 over 5.2. And I'm going to get rid of this natural log by raising this to an e. E to this power gives me A0 divided by 5.2 milligrams per kilogram. And we can go inverse e to the x. It gives me 1.79. A0 divided by 5.2 mgs per kilogram. I'm going to go over here. So I could cross multiply 1.79 times 5.2 times 5.2 equals 9.31. So A initial equals 9.31 milligrams per kilogram. Okay, and that's the answer, 9.3 milligrams per kilogram of body weight. Okay, so I hope those helped. Anyway, over and out.